This is 2.2 Nomenclature and Isomerism Fact File answers. So, number 1. Which of the following is the IUPAC name for the hydrocarbons shown below? What we want to do is identify the longest chain. So, we can look in several directions here. 1, 2, 3, 4. Or we could go 1, 2, 3, 4. Or 1, 2, 3, 4. Now, looking at either the red or the green pathways that I took there, both of those side chains would be attached to the third carbon. But if we look at the blue, we're going 1, 2, 3, 4 for the carbons. So it's going to be both of the methyl groups are attached to number 2. So it's 2,2 dimethyl something. And the something is 1, 2, 3, 4. So it's butane, so that is A, 2,2 dimethylbutane. Question 2. 3-methylpentene, which is given here, exists as geometric stereoisomers. Explain the meaning of the term geometric isomers. So we're looking simply for the same structural formula. But a different spatial arrangement. Okay, so 1 mark for the same structural formula, 1 for saying different spatial arrangement. You could say that they're non-superimposable or that they have different arrangements in 3 dimensions. I give 2 reasons why this compound 3-methylpentene exists as geometric isomers. So the first reason is the restricted rotation. Around the carbon-carbon double bond. And the second reason then is that both carbons in that bond have 2 different atoms. Or groups attached to them. Part 3, draw the E isomer of methylpentene. I'm going to start with the carbon-carbon double bond, and it's 3-methylpentene. So that means we need a CH3 here, and then our C2H5 here, which gives us 1, 2, 3, 4, 5 in the longest carbon chain. 3-methyl, so we've got a CH3 here, and then a hydrogen on this carbon as well. Now draw and name a structural isomer of 3-methylpentene which cannot form geometric isomers. I suppose the simplest one to do is this one here, where we just have 4 methyl groups around that double bond. You could also have it with the double bond where you have like 1, 2, 3, 4. You would have a 4 carbon chain here, so C4, H2, 4, 6, H9, and then hydrogens filling the other bonds around the carbon. Or you could have just with 2 methyl groups, and an ethyl group and a hydrogen on the other carbon. I would go for this one because it is the most obviously the same all over, and definitely not a geometric isomer. So how many structural isomers have the formula C5H12? Well, the answer is 3. And if we just have a look at drawing those out, the first 1, 2, 3, 4, 5 would be like this with 5 carbons in a chain. If we then look at the possibilities for a 4 carbon chain, and we put a methyl group on there, that gives us the right number of carbons. Now it doesn't matter if I was to put it here or here, obviously that's the same molecule, and if I was to put it on one of the end carbons there, it would just take me to the same formula as the one that I drew at the top. And finally the last one, if we go for a 3 carbon chain, we could put the methyl groups in the middle. Again, if I put